The human brain is a marvel of nature. A web of billions of neurons firing in concert allows us to think, learn, and perceive the world. Scientists and engineers have long been inspired by this biological masterpiece. This inspiration has given rise to artificial neural networks. Neural networks are the cornerstone of modern artificial intelligence. They are complex structures, composed of interconnected nodes or neurons. These networks learn from data, identifying patterns and relationships, much like our own brains. With each computation, they adapt and improve, becoming more accurate and efficient. Imagine a child learning to ride a bike. At first, there are wobbles and falls, but through practice and feedback, the child's brain adjusts. Similarly, neural networks adjust their internal parameters, refining their performance on a given task. This ability to learn from experience is what makes them so powerful. From self-driving cars to medical diagnosis, neural networks are transforming our world. They power our virtual assistants, translate languages, and even compose music. As we delve deeper into the realm of AI, understanding these networks becomes increasingly vital. Consider the act of seeing. Light enters our eyes, striking our retinas. This information is then processed by our brains, allowing us to recognize objects and navigate our surroundings. Convolutional neural networks, or CNNs, aim to replicate this process. CNNs are specifically designed for visual data. They excel at tasks like image classification, object detection, and facial recognition. Think of unlocking your phone with your face or a self-driving car navigating a busy street. These feats are made possible by CNNs. These networks employ specialized layers that act as filters, extracting features from images. They learn to identify edges, shapes, and patterns, gradually building a complex understanding of the visual world. This hierarchical approach allows CNNs to handle vast amounts of visual data with remarkable accuracy. The applications of CNNs extend far beyond our everyday lives. In healthcare, they assist doctors in diagnosing diseases from medical images. In astronomy, they help us map distant galaxies and analyze celestial objects. CNNs are the eyes of AI, giving machines the ability to see and interpret the visual world. Language is inherently sequential. Words follow one another, forming sentences, paragraphs, and stories. Understanding the order and context of words is crucial for comprehending language. This is where recurrent neural networks, or RNNs, come into play. RNNs are designed to process sequential data, where the order of information matters. They have a unique ability to remember past inputs, allowing them to understand context and dependencies within a sequence. This makes them ideal for tasks like language translation, speech recognition, and text generation. Imagine a musician composing a symphony. Each note influences the next, creating a harmonious progression. Similarly, RNNs maintain a memory of previous inputs, informing their processing of subsequent data. This memory allows them to capture the nuances of language and generate coherent and contextually relevant text. From chatbots that engage in conversations to voice assistants that respond to our commands, RNNs are revolutionizing the way we interact with machines. They are enabling us to communicate with technology in a more natural and intuitive way, blurring the lines between human and artificial intelligence. While RNNs excel at processing sequences, they often struggle with long-term dependencies. Information from earlier in a sequence can fade as the network processes more data. This is where long short-term memory networks, or LSTMs, come to the rescue. LSTMs are a specialized type of RNN designed to address the vanishing gradient problem. They possess a unique memory cell that acts as a gatekeeper, selectively remembering or forgetting information. This allows them to retain crucial information over long periods, making them ideal for tasks requiring long-term dependencies. Consider reading a novel. You may not remember every detail, but you retain the overarching plot and character development. LSTMs operate similarly, selectively remembering crucial information while discarding irrelevant details. This ability to manage long-term dependencies makes them powerful tools for tasks like machine translation and video captioning. From generating realistic dialogue in chatbots to predicting stock market trends, LSTMs are pushing the boundaries of what's possible with AI. Their ability to learn and remember over extended periods makes them invaluable for tasks requiring a deep understanding of temporal data.